The speed of light, 299,792 kilometers per second, is not just a number. It's a boundary written into the fabric of reality itself. Einstein's theory of relativity tells us this speed isn't just fast, it's final. But why? What makes this particular velocity so special? Could anything lie beyond it? Imagine you're standing on Earth, looking up at the night sky. The light from the nearest star, Proxima Centauri, has traveled for over 4 years just to reach your eyes. The light from distant galaxies has journeyed for billions of years, carrying messages from the ancient universe. This cosmic speed limit shapes everything we see, everything we know, and everything we can ever hope to explore. In this journey through space and time, we won't promise easy answers. We won't claim to know what lies beyond the ultimate speed limit. Instead, we'll explore what physics allows, what it forbids, and where our imagination runs ahead of both. We'll dive deep into the mysteries that have puzzled scientists for over a century, and we'll ask the questions that keep physicists awake at night. The speed of light is more than just how fast photons travel. It's the speed of causality itself, the rate at which cause and effect can propagate through the universe. It's the cosmic speed limit that keeps the past in the past and the future in the future. Without it, the very concept of time as we understand it would crumble. But human curiosity has never been satisfied with limits. We dream of faster than light travel, of warp drives and wormholes, of reaching distant stars in human lifetimes rather than geological ages. These dreams push us to the very edge of what physics might allow, into realms where mathematics becomes strange and reality itself seems to bend. Consider the implications of this speed limit. When you look at the sun, you're seeing it as it was 8 minutes ago. When you observe Jupiter, you're witnessing events that happened between 33 and 54 minutes in the past, depending on where Earth and Jupiter are in their orbits. The Andromeda Galaxy, our nearest galactic neighbor, shows us light that began its journey 2.5 million years ago, when early humans were just beginning to walk upright on the African plains. This delay isn't just a curiosity, it's fundamental to how information flows through the universe. Nothing, not matter, not energy, not even information itself, can travel faster than light. This creates a cosmic horizon beyond which we cannot see or communicate. It means that if something dramatic happened right now on a planet orbiting Alpha Centauri, we wouldn't know about it for over 4 years. Yet throughout human history, we've consistently found ways to transcend what seemed like absolute limits. We learned to fly when flight seemed impossible. We split the atom when atoms were thought to be indivisible. We sent signals across the globe instantly when such communication was pure fantasy. Could the speed of light be just another barrier waiting to be broken? The question becomes even more intriguing when we consider that the early universe itself seemed to violate this speed limit. During cosmic inflation, space itself expanded faster than light could travel through it. If the universe could do it once, might we find a way to do it again? The mathematics of general relativity suggest tantalizing possibilities, theoretical constructs like wormholes and warp drives that could potentially allow faster than light travel without technically violating Einstein's prohibition. But these possibilities come with profound challenges and paradoxes. If we could travel faster than light, we might be able to travel backward in time, creating logical contradictions that could unravel the very fabric of causality. We might find ourselves in a universe where effects could precede their causes, where the future could influence the past, where the orderly flow of time itself could become a chaotic tangle. Tonight, we'll journey to that edge together. We'll explore the fundamental laws that govern our universe, the speculative technologies that might one day transcend them, and the profound implications of what might happen if we ever find a way beyond the speed of light. Whether such a breakthrough is possible, impossible, or something in between, the very act of exploring these questions reveals the boundless nature of human imagination. We'll meet the scientists who first discovered this cosmic speed limit, examine the mathematics that defines it, and peer into the speculative realm where physicists dare to imagine what might lie beyond. We'll consider not just the technical challenges, but the philosophical and ethical implications of transcending what may be the universe's most fundamental boundary. So settle in as we embark on this cosmic adventure, where the only thing faster than light might be the speed of human curiosity itself. To understand why nothing can travel faster than light, we must first understand what light truly is. Light isn't just the glow from a bulb or the warmth from the sun. It's electromagnetic radiation, a fundamental force of nature that permeates every corner of the universe. When we talk about the speed of light, we're really talking about the speed at which all electromagnetic phenomena propagate through space. But here's where things get interesting. The speed of light isn't actually about light at all. It's about the structure of space and time itself. Even if light didn't exist, this speed limit would still be there, woven into the very fabric of reality. It's the speed at which causality propagates, the maximum rate at which any cause can produce an effect anywhere in the universe. Albert Einstein discovered this in 1905, though he didn't set out to find a cosmic speed limit. He was trying to resolve a puzzle about electromagnetic waves. The equations describing electricity and magnetism, worked out by James Clerk Maxwell decades earlier, predicted that electromagnetic waves should travel at a specific speed. But speed relative to what? When you throw a ball from a moving train, the ball's speed depends on whether you measure it from the train or from the ground. Maxwell's equations suggested that light should behave differently. Einstein's breakthrough was realizing that the speed of light is the same for everyone, everywhere, no matter how fast they're moving. This sounds simple, but it overturned our understanding of space and time. If the speed of light is constant, then space and time themselves must be flexible. As you move faster through space, time slows down. As you approach the speed of light, time nearly stops. This leads us to one of the most profound insights in physics: time dilation. Imagine you're on a spacecraft accelerating toward the speed of light. To you, inside the ship, everything seems normal. Your watch ticks at the same rate, your heartbeat remains steady, your thoughts flow at their usual pace. But to someone watching from Earth, your time has slowed to a crawl. What feels like minutes to you might be hours, days, or even years to the outside observer. The mathematics behind this isn't just theoretical. We see time dilation in particle accelerators, where subatomic particles racing at nearly the speed of light live much longer than they should. We account for it in GPS satellites, whose clocks run slightly fast compared to Earth-based clocks because they're moving at high speeds and experiencing weaker gravity. Without correcting for these effects, GPS would be useless within hours. But time dilation is just the beginning. As you approach the speed of light, something even stranger happens to mass and energy. Einstein showed us that mass and energy are two sides of the same coin, related by his famous equation E equals mc squared. As you accelerate, your kinetic energy increases. But according to relativity, this energy contributes to your mass. The faster you go, the more massive you become. This creates a vicious cycle. As you get more massive, you need more force to accelerate further. As you need more force, you need more energy. As you approach the speed of light, your mass approaches infinity, and so does the energy required to accelerate you further. To actually reach the speed of light, you would need infinite energy, which is impossible to obtain. This is why nothing with mass can ever reach the speed of light, let alone exceed it. It's not a limitation of our technology or our understanding. It's a fundamental property of the universe itself. The speed of light isn't just fast, it's unreachable for anything that has mass. But what about things that don't have mass? Light itself consists of photons, which are massless particles. They don't gradually accelerate to the speed of light, they're created moving at that speed and can never slow down or speed up. In a sense, photons exist outside of time. From a photon's perspective, if such a thing makes sense, its journey from a distant star to your eye happens instantaneously, even though it might take billions of years from our perspective. This brings us to another crucial insight. The speed of light isn't really the speed of light at all. It's the speed of space-time itself. It's the conversion factor between space and time, the exchange rate that determines how much time equals how much space. In the equations of relativity, space and time are unified into a single entity called space-time, and the speed of light is simply the speed at which changes propagate through this unified fabric. Consider what this means for information. Nothing can carry information faster than light. Even if we could somehow create a rigid rod stretching from Earth to Alpha Centauri, pushing one end wouldn't instantly move the other end. The push would propagate through the rod at the speed of sound in the rod material, which is much slower than light. No signal, no message, no information of any kind can travel faster than light speed. This creates what physicists call the light cone, a geometric representation of what events can influence what other events in spacetime. Imagine a cone extending from any point in spacetime. The surface of the cone represents the paths that light rays can take. Anything inside the cone can potentially influence or be influenced by the event at the cone's tip. Anything outside the cone is causally disconnected, forever beyond the reach of influence. The implications are staggering. Right now, as you listen to these words, there are events happening throughout the universe that cannot possibly affect you, no matter what they are. A star could explode in a distant galaxy. A civilization could send messages into space. Entire worlds could be born or destroyed. And if they're far enough away, these events exist in a realm beyond causality, beyond the reach of influence. This is the cosmic censorship that the speed of light imposes on the universe. It prevents the chaos that would result if distant events could instantly affect nearby ones. It maintains the orderly flow of cause and effect that makes physical law possible. Without this speed limit, the universe would be a place where effects could precede their causes, where logic itself might break down. Yet, even as we understand these limits, we can't help but wonder about their edges. Relativity tells us that massive objects can't reach light speed. But what about the fabric of space itself? During cosmic inflation, space expanded faster than light, carrying distant regions of the universe beyond each other's light cones. If space can expand faster than light, might there be other ways to effectively travel faster than light without actually moving through space at that speed? These questions push us to the very boundaries of known physics, into realms where our current understanding becomes murky and speculative. They force us to confront the possibility that the speed of light, while fundamental, might not be the final word on cosmic speed limits. But to explore these possibilities, we must first understand what it might mean to go beyond the speed of light, and what consequences such travel might have for the very structure of reality itself. Let's delve deeper into the mathematical beauty of these limits. The Lorentz transformation, named after Dutch physicist Hendrik Lorentz, describes exactly how space and time change as you approach light speed. These equations show that as your velocity approaches the speed of light, your length contracts in the direction of motion, your time dilates, and your mass increases. But these aren't just mathematical curiosities. They're descriptions of how reality itself behaves. The length contraction is particularly fascinating. A ruler moving at 90% the speed of light would appear to shrink to less than half its original length to a stationary observer. At 99% light speed, it would contract to just 14% of its original length. As you approach light speed, you would literally flatten into a pancake from the perspective of someone watching you pass by. But here's the strange part. You wouldn't feel any of this happening. From your perspective, you remain perfectly normal. It's the rest of the universe that appears contracted and time dilated. This reciprocity is one of the most counterintuitive aspects of relativity. There's no absolute reference frame, no cosmic measuring stick against which all motion can be judged. Everything is relative to everything else. This relativistic framework has been tested countless times and has never failed. When particles in accelerators approach light speed, they behave exactly as Einstein predicted. When atomic clocks fly on airplanes, they keep time exactly as relativity demands. When we observe distant galaxies, we see the effects of time dilation in their light. The universe consistently confirms that the speed of light is indeed an absolute limit for anything with mass. But what about massless particles? Photons, the particles of light, have zero rest mass. They exist only in motion, always traveling at exactly the speed of light. From our perspective, a photon's journey from the sun to Earth takes about 8 minutes. But from the photon's perspective, the journey is instantaneous. Time doesn't exist for a photon. It's created and absorbed in the same moment of its own experience. This leads to one of the most profound insights about the nature of reality. The universe looks very different depending on your speed. At everyday speeds, space and time seem fixed and absolute. But as you approach light speed, the universe transforms into something almost unrecognizable. Distances shrink, time stretches, and the familiar 3 dimensions of space merge with the single dimension of time into a unified 4-dimensional space-time. Einstein's general relativity, developed a decade after special relativity, revealed that this space-time isn't just a passive stage where physics plays out. It's a dynamic entity that can be curved and warped by matter and energy. This curvature is what we experience as gravity. The Earth doesn't pull you down with a mysterious force. It warps space-time in such a way that your natural motion through curved space-time appears as falling. This geometric view of gravity has profound implications for the speed of light. In curved space-time, light still travels at the speed of light locally, but its path through the universe can be bent and twisted. Light rays follow geodesics, the straightest possible paths through curved space-time. When light passes near a massive object like the sun, space-time curvature bends its path, creating the phenomenon we call gravitational lensing. But even in curved space-time, the local speed of light remains constant. No matter how strongly gravity warps space and time, light always travels at 299,792 kilometers per second when measured locally. This constancy is built into the very structure of space-time itself. The mathematical framework of relativity also reveals something else. The speed of light is connected to the fundamental constants of nature. In the equations of electromagnetism, the speed of light emerges from the relationship between the electric permittivity and magnetic permeability of free space. These aren't arbitrary numbers, they're fundamental properties of the vacuum itself. This connection runs deeper than you might expect. The speed of light appears in quantum mechanics, in the equations describing the strong nuclear force, in the mathematics of black holes, and in cosmology. It's not just the speed at which light travels, it's a fundamental constant that determines the basic structure of physical law. Consider the implications for the possibility of faster than light travel. If the speed of light is truly fundamental, then exceeding it wouldn't just be difficult, it would require changing the basic constants of nature. This would be like trying to make 2 + 2 = 5, not just in mathematics, but in the physical structure of reality itself. Yet, even as we understand these profound limits, we can't help but notice the subtle ways that nature seems to bend them. Virtual particles in quantum field theory can briefly exceed light speed, though they can never be directly observed. Quantum entanglement allows instant correlations between distant particles, though this can't be used to send information faster than light. The expansion of space itself can carry distant regions of the universe away from each other faster than light. These phenomena don't violate relativity, they reveal its subtle boundaries. They show us that while nothing can move through space faster than light, there might be ways to manipulate space itself. They hint at possibilities that exist at the very edge of theoretical physics, where our understanding becomes uncertain and our mathematics pushes into uncharted territory. The speed of light also has practical implications for space exploration. The nearest star system, Alpha Centauri, is about 4 1/3 light-years away. Even traveling at 10% the speed of light, an incredibly fast speed by today's standards, the journey would take over 43 years. At 1% light speed, it would take over 4 centuries. These distances reveal the true scale of cosmic isolation imposed by the speed of light. But perhaps the most profound implication is philosophical. The speed of light doesn't just limit how fast we can travel, it limits how fast information can propagate. This creates a fundamental granularity to causality itself. Events that happen simultaneously in one reference frame might happen at different times in another. The very concept of now becomes relative and depends on your motion through space-time. This challenges our intuitive understanding of time and causality. We like to think of the universe as having a single, universal now that applies everywhere, but relativity shows us that simultaneity is relative. What counts as now depends on your reference frame. 2 events that seem simultaneous to you might occur at different times to someone moving relative to you. These insights forced physicists to abandon the comfortable notion of absolute time that had guided scientific thinking for centuries. Instead, we had to accept a universe where time and space are intimately connected, where the speed of light serves as the cosmic speed limit, not just for matter and energy, but for causality itself. The speed of light stands as perhaps the most fundamental limit in physics. It's not just a speed limit for objects moving through space, it's a limit on how fast cause and effect can propagate through the universe. It maintains the logical structure of causality that makes physical law possible. Without this limit, the universe would be a chaotic place where effects could precede their causes and logical contradictions could arise. Though physics sets these limits with mathematical precision, human curiosity pushes us to imagine how, if ever, they might be bent or transcended. The speed of light stands as both barrier and beacon, defining the boundaries of the possible while illuminating the questions that drive us to explore beyond them. Despite the seemingly insurmountable barrier that the speed of light presents, human imagination has never stopped dreaming of ways to transcend it. From the pages of science fiction to the equations of theoretical physics, the possibility of faster than light travel continues to captivate minds and challenge our understanding of what might be possible in our universe. The dream isn't just about speed, it's about connection. The vast distances between stars create an isolation so profound that even light, the fastest thing in the universe, takes years to bridge the gaps. If we could somehow exceed light speed, we could transform the cosmos from a collection of isolated islands into a connected archipelago of worlds. We could explore distant galaxies, communicate with alien civilizations, and perhaps even travel backward in time. But is faster than light travel merely the stuff of fantasy? Or could there be legitimate scientific pathways to achieving it? The answer, as with many things in physics, is both more complex and more fascinating than you might expect. Let's start with the most famous speculative concept, the Alcubierre drive. In 1994, Mexican physicist Miguel Alcubierre published a paper that sent shockwaves through the scientific community. He showed that Einstein's equations of general relativity might, under certain conditions, permit a form of faster-than-light travel. The Alcubierre drive doesn't propel a spacecraft through space at faster-than-light speeds. Instead, it manipulates space itself. The concept involves contracting space in front of a spacecraft while expanding space behind it. The ship itself never moves faster than light through the space immediately around it, but the manipulation of space-time carries it to its destination faster than light could travel through normal space. Imagine you're standing on a moving walkway at an airport. You might be walking at your normal pace, but the walkway carries you forward faster than you could walk alone. The Alcubierre drive would work similarly, except instead of a walkway, it would manipulate the fabric of space-time itself. The mathematics are elegant and surprisingly straightforward. Alcubierre's equations show that space-time can be warped in such a way that the proper distance between 2 points shrinks in front of the spacecraft and expands behind it. From the perspective of someone outside this warped region, the spacecraft appears to travel faster than light. But from the spacecraft's perspective, it's simply riding a wave of compressed and expanded space-time. This isn't just mathematical speculation. The concept builds on well-established physics. We know that space can expand faster than light because we observe it happening in cosmic inflation and in the current expansion of the universe. Distant galaxies are moving away from us faster than light, not because they're moving through space at those speeds, but because space itself is expanding between us and them. If space can expand faster than light naturally, then perhaps we could learn to manipulate it artificially. The Alcubierre drive represents a mathematically consistent way to do exactly that. The equations work, the physics is sound, and the concept doesn't violate any known laws of nature. But here's where the dream meets reality. The energy requirements are staggering. Early calculations suggested that creating an Alcubierre drive would require more energy than exists in the observable universe. The exotic matter needed to warp space-time in the required way would have to have negative energy density, something that might not exist in nature. However, subsequent research has shown ways to dramatically reduce these energy requirements. Chris van den Broek showed that by adjusting the shape of the warp bubble, the energy requirements could be reduced to the mass energy equivalent of a few suns. Still enormous, but at least within the realm of what an advanced civilization might theoretically achieve. More recent work has pushed the energy requirements even lower. Some proposals suggest that the energy needed might be reduced to something equivalent to the mass of a large asteroid, or even a spacecraft itself. While still far beyond our current capabilities, these aren't the universe-breaking energy requirements of the original design. The key insight is that the shape and structure of the warp bubble matters enormously. Small changes in the geometry can lead to dramatic reductions in energy requirements. This suggests that there might be optimal configurations we haven't yet discovered, ways to achieve warp drive with energy requirements that an advanced civilization could realistically meet. But even if we could solve the energy problem, other challenges remain. The exotic matter required for the drive would need to have negative energy density, creating a region of space-time with less energy than empty space. While quantum field theory suggests that such negative energy states might exist, we've never observed them on the macroscopic scale that would be required for a warp drive. There's also the question of stability. Would an Alcubierre drive be stable once created, or would it collapse under its own exotic properties? Computer simulations suggest that maintaining the delicate balance of forces required for the drive would be extraordinarily difficult. The slightest perturbation could cause the warp bubble to collapse, potentially with catastrophic consequences. Then there's the navigation problem. How do you steer something that's riding a wave of warped space-time? How do you start and stop the drive? How do you prevent the intense tidal forces from tearing apart anything inside the warp bubble? These engineering challenges are formidable, even if we assume the underlying physics is sound. Perhaps most troubling is the causality problem. If you can travel faster than light, you can potentially travel backward in time. This opens up all sorts of paradoxes and logical contradictions that might make faster than light travel fundamentally impossible, regardless of the energy requirements. But the Alcubierre drive isn't the only speculative pathway to faster than light travel. Another possibility lies in the concept of traversable wormholes. These hypothetical shortcuts through space-time could potentially connect distant regions of the universe, allowing faster than light travel without technically exceeding the speed of light. A wormhole is essentially a tunnel through space-time. Imagine folding a piece of paper and poking a hole through both layers. An ant walking on the paper could travel from one side to the other, either by walking across the surface or by going through the hole. The hole represents a much shorter path, even though the ant never travels faster than its normal walking speed. Einstein and Nathan Rosen first described these space-time tunnels in 1935. They showed that the equations of general relativity permit bridges connecting distant regions of space-time. However, these Einstein-Rosen bridges are extremely unstable and would collapse faster than light could travel through them. To create a stable, traversable wormhole, you would need to thread it with exotic matter to keep it open. This exotic matter would need to violate the null energy condition, having negative energy density similar to what's required for the Alcubierre drive. The energy requirements are similarly astronomical, but the concept is mathematically consistent with known physics. Interestingly, some theories suggest that wormholes might occur naturally in the quantum foam of spacetime. At the Planck scale, the smallest meaningful scale in physics, spacetime itself might be riddled with tiny wormholes constantly forming and dissolving. If we could somehow enlarge and stabilize these microscopic wormholes, we might create macroscopic passages through spacetime. Another approach involves the manipulation of extra dimensions. String theory and other advanced theories suggest that our universe might have more than the 4 dimensions we experience. If these extra dimensions exist, they might provide shortcuts through higher dimensional space that could effectively allow faster than light travel in our 3-dimensional world. Think of it like this. If you're walking on a curved surface, the shortest path between 2 points might not be a straight line on that surface. It might be a chord cutting through the higher dimensional space in which the surface is embedded. Similarly, if our universe is embedded in a higher dimensional space, there might be shortcuts through those extra dimensions that could dramatically reduce travel times. The concept of cosmic inflation also offers tantalizing hints about faster than light possibilities. During the first fraction of a second after the Big Bang, space itself expanded faster than light. This expansion didn't violate relativity because it wasn't matter or energy moving through space. It was space itself expanding. If cosmic inflation could happen naturally, perhaps we could learn to trigger it artificially. Instead of expanding all of space, we might find ways to create localized regions of accelerated expansion. This could potentially allow for faster than light travel without requiring exotic matter or violating causality. Some physicists have proposed that vacuum decay, the transition from our current vacuum state to a lower energy state, might create expanding bubbles of space with different physical properties. If we could somehow ride the boundary of such a bubble, we might achieve faster than light travel. However, vacuum decay would likely be catastrophic for any existing matter, making this approach both dangerous and impractical. Quantum mechanics adds another layer of complexity to these possibilities. Quantum entanglement creates instantaneous correlations between particles, regardless of the distance separating them. While this can't be used to send information faster than light, it suggests that the universe has mechanisms for instantaneous action at a distance. Some speculative theories propose that we might be able to exploit quantum entanglement for communication or travel. If we could create entangled states between distant locations, we might be able to use these quantum correlations to transfer information or even matter instantaneously across vast distances. The concept of quantum tunneling also offers intriguing possibilities. In quantum mechanics, particles can tunnel through barriers that would be impossible to cross classically. Some theories suggest that macroscopic objects might be able to quantum tunnel through the barriers imposed by relativity, potentially allowing faster than light travel. However, the probability of macroscopic quantum tunneling is astronomically small. You would need to wait longer than the age of the universe for even a single atom to tunnel through a barrier of any significant size. For a spacecraft, the waiting time would be incomprehensibly vast. Recent developments in quantum field theory have revealed other interesting possibilities. The Casimir effect shows that quantum fluctuations in the vacuum can create measurable forces between closely spaced objects. Some theories suggest that these quantum effects might be manipulated to create the negative energy densities required for warp drives or wormholes. Advanced propulsion concepts like the M-drive have claimed to generate thrust without propellant, potentially by manipulating quantum vacuum fluctuations. While these claims remain highly controversial and have not been conclusively verified, they represent the kind of thinking that might eventually lead to breakthrough propulsion technologies. The concept of metamaterials also offers new possibilities. These artificially structured materials can manipulate electromagnetic fields in ways that don't occur naturally. Some researchers have proposed that metamaterials might be used to create regions of space with negative refractive indices, potentially allowing faster than light propagation of electromagnetic waves. Even more speculative are proposals involving the manipulation of consciousness or information itself. Some interpretations of quantum mechanics suggest that consciousness plays a fundamental role in the collapse of quantum wave functions. If consciousness could somehow be transmitted faster than light, it might allow for instantaneous communication or travel. The concept of digital physics, which suggests that the universe is fundamentally computational, opens up other possibilities. If reality is indeed a form of computation, there might be ways to exploit the underlying computational substrate to achieve faster than light effects. As we explore these speculative possibilities, it's important to remember that they exist at the very edge of theoretical physics. They represent mathematical curiosities and thought experiments rather than practical technologies. The energy requirements are enormous, the engineering challenges are staggering, and many of these concepts may turn out to be physically impossible for reasons we don't yet understand. Yet the fact that these possibilities exist at all, that they're consistent with known physics and mathematics, suggests that the speed of light barrier might not be as absolute as it appears. Nature has surprised us before with phenomena that seemed impossible until we understood them better. Perhaps faster than light travel will join the ranks of human flight, space travel, and quantum computing, as impossible things that became possible once we understood the underlying principles. The mathematical consistency of these concepts doesn't guarantee their practicality, but it does suggest that the universe might be more flexible than our everyday experience suggests. The speed of light remains a formidable barrier, but it might not be an absolute one. Though these ideas are mathematically valid, they remain practically impossible for now. The energy requirements, the need for exotic matter, and the engineering challenges place them far beyond our current capabilities. But human ingenuity has a history of turning impossible dreams into everyday realities, and the mathematics of faster than light travel suggest that this particular dream might not be forever beyond our reach. Speculation about bending space and time leads us to deeper puzzles about the nature of causality itself and what would happen to the fundamental structure of reality if we could somehow transcend the cosmic speed limit. The dream of faster-than-light travel becomes a nightmare when we consider its implications for the fundamental structure of reality. What seems like a simple matter of going faster than light turns out to threaten the very foundation of logical thinking. The principle that causes must precede their effects. This isn't just a technical problem to be solved. It's a potential unraveling of the coherent structure that makes physics possible. To understand why faster-than-light travel creates such profound problems, we need to explore the strange relationship between space, time, and causality. In our everyday experience, time flows uniformly forward. Causes always precede effects, and the sequence of events is the same for everyone. But Einstein's relativity reveals that this comfortable picture is an illusion created by our slow speeds and limited perspective. The problem begins with the relativity of simultaneity. Events that appear simultaneous to one observer may occur at different times for another observer moving at a different velocity. This isn't just a matter of perception or measurement error, it's a fundamental property of space-time itself. What counts as now depends entirely on your reference frame. Imagine two lightning strikes hitting opposite ends of a moving train. To someone standing on the platform, the strikes might appear perfectly simultaneous. But to someone riding on the train, one strike will appear to happen before the other. Neither observer is wrong. Simultaneity is simply relative. This relativity of simultaneity is one of the most counterintuitive consequences of Einstein's theory, but it's been confirmed countless times in laboratory experiments. Now here's where faster-than-light travel creates havoc with causality. If you can travel faster than light, you can exploit the relativity of simultaneity to create scenarios where effects precede their causes. You can potentially influence events in your own past, creating logical paradoxes that threaten the consistency of physical law itself. Let's walk through a concrete example. Suppose you have a faster-than-light communicator that can send messages instantaneously across space. You send a message from Earth to a space station orbiting Alpha Centauri, 4 1/3 light-years away. The message arrives instantly from your perspective. But from the perspective of the space station, which is moving relative to Earth, your message might arrive before you sent it. This creates the possibility of a causal loop. The space station could immediately send a reply back to Earth. From the station's reference frame, this reply is being sent after they received your message. But from Earth's reference frame, this reply might arrive before you sent the original message. You could receive a reply to a message you haven't sent yet. This isn't just a curiosity, it opens the door to grandfather paradox type scenarios on a cosmic scale. You could send yourself a message warning about some future disaster, then take action to prevent that disaster, which would eliminate the reason for sending the warning in the first place. The logical contradictions multiply like a virus, potentially making consistent physics impossible. The mathematical framework that describes these paradoxes is both elegant and disturbing. The light cones that define causality in space-time become tangled when faster-than-light travel is introduced. Events that should be causally disconnected become connected, creating closed time-like curves where an event can influence its own past. Some physicists have proposed that nature might have built-in safeguards against these paradoxes. The Novikov self-consistency principle suggests that any action you take in the past was always part of history. If you travel back in time to prevent a disaster, your intervention was always the reason the disaster didn't happen in the first place. The universe maintains logical consistency by ensuring that time travel creates self-fulfilling prophecies rather than paradoxes. But this solution creates its own problems. If the universe somehow enforces self-consistency, it suggests that free will might be an illusion. Your actions in the past would be predetermined by the need to maintain logical consistency. This deterministic view of time travel preserves causality, but at the cost of undermining our understanding of choice and agency. Another proposed solution is the many worlds interpretation of quantum mechanics. If every possible outcome of every quantum event creates a separate universe, then time travel doesn't change the past. It simply moves you to a different universe where events unfolded differently. You could travel back and prevent your grandfather from meeting your grandmother, but you would end up in a universe where you were never born, while your original universe remains unchanged. This multiverse solution preserves logical consistency, but creates its own puzzles. If time travel moves you between universes, are you really traveling through time, or are you simply moving between parallel realities? And if infinite universes exist containing every possible outcome, what meaning does causality have anyway? The concept of tachyons adds another layer of complexity to these causality problems. Tachyons are hypothetical particles that always travel faster than light. They're the mathematical opposite of normal particles, existing only at speeds greater than light speed. While normal particles approach infinite energy as they approach light speed, tachyons would approach infinite energy as they slow down toward light speed. From a mathematical perspective, tachyons are consistent with relativity. The equations allow for particles with imaginary mass that would always travel faster than light. But tachyons create immediate causality problems. They would allow information to travel backward in time, enabling all the paradoxes associated with faster than light communication. Moreover, tachyons would make the vacuum unstable. If tachyons existed, they would constantly be emitted by ordinary matter, carrying away energy until everything in the universe decayed to the lowest possible energy state. The fact that we don't observe this runaway decay is often cited as evidence that tachyons don't exist in nature. Some theories attempt to resolve the tachyon problem by suggesting that they exist in a separate sector of physics, unable to interact with ordinary matter. This would preserve the mathematical consistency of relativity while avoiding the paradoxes. But it also makes tachyons completely unobservable and therefore irrelevant to practical faster-than-light travel. The quantum mechanical phenomenon of entanglement presents an interesting case study in faster-than-light correlations that don't violate causality. When two particles become entangled, measuring one instantly affects the other, regardless of the distance between them. This spooky action at a distance troubled Einstein, who saw it as a violation of locality and potentially causality. However, quantum entanglement doesn't allow faster-than-light communication. The correlations between entangled particles are instantaneous, but they can't be used to send information. When you measure an entangled particle, you get a random result. The correlation with its partner is perfect, but since both results are random, no information passes between them. This no communication theorem is fundamental to quantum mechanics. It ensures that quantum entanglement, while creating instantaneous correlations, doesn't violate causality or allow information to travel faster than light. The universe seems to have found a way to allow instantaneous connections while preserving the logical structure of cause and effect. Some interpretations of quantum mechanics suggest that these correlations don't involve any kind of signal or influence traveling between particles. Instead, entangled particles might be better understood as a single quantum system that happens to be spread across space. The correlation isn't a result of communication, but rather a reflection of the fundamental non-local nature of quantum reality. The measurement problem in quantum mechanics adds another twist to causality questions. If consciousness plays a role in quantum measurement, as some interpretations suggest, then the act of observation might have faster-than-light effects. But again, this doesn't allow for information transfer or communication faster than light. Recent experiments have confirmed that quantum correlations are indeed instantaneous, at least within the precision of our measurements. But they've also confirmed that these correlations can't be used for faster-than-light communication. Nature seems to walk a fine line. allowing instantaneous connections while preserving causality. The concept of closed time-like curves, solutions to Einstein's equations that allow travel into the past, represents the most direct challenge to causality in theoretical physics. These curves exist in certain exotic space-time geometries, such as those containing rotating black holes or cosmic strings. While they're mathematically consistent with general relativity, they create obvious paradoxes if they could be traversed. The Gödel universe, proposed by mathematician Kurt Gödel in 1949, contains closed time-like curves throughout space-time. In such a universe, every point could potentially be connected to its own past, making causality meaningless. Fortunately, our universe doesn't appear to have the global rotation required for Gödel's solution. Other solutions, like the Morris-Thorne wormholes, could theoretically allow time travel if constructed with specific properties. A traversable wormhole connecting two regions of space could become a time machine if one end is accelerated to high speeds and then returned. The time dilation experienced by the moving end would create a time difference between the two mouths of the wormhole. But even these theoretical time machines might be prevented by quantum effects. Stephen Hawking proposed the chronology protection conjecture, suggesting that quantum fluctuations would become infinite near any closed time-like curve, preventing its formation. The universe might have built-in mechanisms to prevent time travel and preserve causality. The conjecture remains unproven, but it reflects a deep intuition among physicists that causality is too fundamental to be violated. If time travel were possible, it would undermine the entire scientific method, which depends on the assumption that causes precede effects and that consistent physical laws govern the universe. Some approaches to quantum gravity, the attempt to unify general relativity with quantum mechanics, suggest that space-time itself might have a discrete structure at the smallest scales. If space-time is quantized, like a digital grid, rather than a smooth continuum, it might prevent the formation of closed time-like curves and preserve causality at a fundamental level. Loop quantum gravity, one approach to quantum gravity, suggests that space-time has a granular structure at the Planck scale. This granularity might prevent the extreme curvatures required for time travel, effectively protecting causality by limiting how severely space-time can be warped. String theory offers a different perspective on causality protection. In string theory, the fundamental objects are extended strings rather than point particles. The extended nature of strings might prevent the formation of the singularities and close time-like curves that threaten causality in point particle theories. The holographic principle, emerging from black hole physics and string theory, suggests that all the information in a volume of space can be encoded on its boundary. This principle might impose fundamental limits on information transfer that could protect causality even in exotic space-time geometries. Despite these theoretical protections, the mathematics of general relativity clearly allows for scenarios that violate causality. This creates a tension between our mathematical theories and our physical intuitions about the nature of time and causation. Either our theories are incomplete, or nature has mechanisms we don't yet understand to prevent causality violations. The anthropic principle offers another perspective on these problems. Perhaps we live in a universe where causality is preserved simply because universes with causality violations are unstable or incompatible with the existence of observers. If causality violations make complex structures like stars, planets, and life impossible, then we naturally find ourselves in a universe where such violations don't occur. This anthropic argument doesn't explain how causality is protected, but it suggests why we might observe a universe where it appears to be protected. Just as we don't find ourselves in universes where the laws of physics prevent the formation of atoms or stars, we might not find ourselves in universes where causality violations prevent the formation of consistent physical law. The implications of causality violations extend beyond physics into philosophy and logic. If effects could precede their causes, the entire framework of rational thinking would be threatened. Science depends on the assumption that we can trace effects back to their causes and use this understanding to predict future outcomes. Causality violations would make this impossible. Even more fundamentally, causality violations challenge our understanding of identity and existence. If you could travel back in time and change the past, in what sense would you still be the same person? If multiple timelines exist simultaneously, which one represents the real you? These questions push us beyond physics into deep philosophical territory about the nature of self and reality. The energy requirements for creating causality-violating scenarios are typically enormous, often requiring exotic matter with negative energy density or black holes with precisely tuned properties. This might represent another form of causality protection. Nature makes causality violations so difficult to achieve that they remain purely theoretical. But perhaps the most profound protection against causality violations is logical consistency itself. If the universe is fundamentally logical, then it might simply be impossible for contradictory states to exist. Causality violations create logical contradictions, and a logically consistent universe might prevent them by its very nature. As we contemplate these deep puzzles about time, causality, and faster-than-light travel, we're forced to confront the possibility that some of our most cherished dreams about transcending physical limits might be fundamentally impossible. The speed of light barrier might exist not just to limit our motion through space, but to preserve the logical structure that makes reality comprehensible. Even if physics allowed such travel, manipulating space and time brings its own monumental challenges that push us to the very edge of what might be theoretically possible, let alone practically achievable, in any conceivable future. To understand our limits in transcending the speed of light, we must dive deeper into the very fabric of reality itself. Space and time aren't just the stage where physics plays out. They're dynamic participants in every physical process. They can stretch, compress, curve, and even tear under the right conditions. Understanding the structure of space-time reveals both why faster-than-light travel seems impossible and where the subtle loopholes might exist. Einstein's greatest insight was recognizing that space and time are unified into a single entity called space-time. This isn't just a mathematical convenience, it reflects a deep truth about the nature of reality. What we perceive as separate dimensions of space and a separate dimension of time are actually different aspects of a four-dimensional continuum that can be rotated, mixed, and transformed. In everyday life, we think of space as fixed and time as flowing. We imagine a universal now that advances uniformly throughout the universe. But this picture is profoundly wrong. Space and time are intimately connected, and their relationship depends on motion and gravity. What seems like pure spatial separation to one observer might be a mixture of spatial and temporal separation to another. The mathematics of space-time geometry reveals that massive objects don't just sit in space-time, they actively warp it. The sun doesn't pull Earth with a mysterious force across empty space. It curves space-time in such a way that Earth follows the straightest possible path through that curved geometry. Gravity isn't a force, it's the curvature of space-time itself. This geometric view of gravity has profound implications for faster-than-light travel. If we could somehow create the right kind of space-time curvature, we might be able to manipulate the geometry of space itself. Instead of trying to accelerate through space faster than light, we might be able to bring distant destinations closer by manipulating the space between them. The energy required to warp space-time significantly is staggering. Consider the Sun, which contains 99.8% of all the mass in our solar system. Its enormous mass creates a relatively modest curvature in space-time, bending light rays by less than 2 arc-seconds as they pass near its edge. To create the dramatic space-time warping required for faster-than-light travel would require energies vastly greater than anything available to us. The Einstein field equations, which describe how matter and energy curve space-time, reveal the mathematical relationship between energy and curvature. The amount of curvature is proportional to the energy density of matter and radiation. To create a warp drive or wormhole, you would need energy densities that approach or exceed those found in the cores of neutron stars or the event horizons of black holes. But it's not just the amount of energy that matters. It's the type of energy. The exotic matter required for most faster-than-light travel schemes would need to have negative energy density. This means it would contain less energy than empty space itself, creating regions of space-time with bizarre properties that we've never observed in nature. Quantum field theory suggests that negative energy densities might be possible under certain circumstances. The Casimir effect demonstrates that quantum fluctuations can create regions where the vacuum energy is lower than its average value. Two metal plates placed very close together in vacuum will attract each other because the quantum fluctuations between them have lower energy than the fluctuations outside. However, the Casimir effect produces only tiny amounts of negative energy, nowhere near what would be required for macroscopic manipulation of spacetime. Moreover, quantum field theory places strict limits on how much negative energy can be concentrated in a given region. These quantum inequalities suggest that large amounts of negative energy might be fundamentally impossible to create or maintain. The structure of spacetime at quantum scales adds another layer of complexity to these problems. At distances approaching the Planck length, about 10 to the minus 35 meters, quantum effects become so strong that our classical picture of smooth spacetime breaks down. At these scales, spacetime itself might have a foam-like structure, constantly fluctuating and changing. These quantum fluctuations of spacetime create virtual particles that briefly pop into existence before annihilating each other. The energy associated with these fluctuations is enormous, potentially infinite if not properly regulated by the mathematics of quantum field theory. Any attempt to manipulate spacetime on macroscopic scales would have to contend with these violent quantum fluctuations. Loop quantum gravity, one approach to describing quantum spacetime, suggests that space and time are made up of discrete, indivisible units. Just as matter is composed of atoms, spacetime might be composed of tiny loops and nodes connected in a complex network. This quantized structure would place fundamental limits on how severely spacetime could be curved or manipulated. If spacetime has a granular structure at the Planck scale, it might be impossible to create the smooth, exotic spacetime geometries required for warp drives or wormholes. The discrete nature of quantum spacetime might prevent the formation of the precisely tuned curvatures that these propulsion schemes require. String theory offers a different perspective on the structure of spacetime. In string theory, the fundamental constituents of reality are one-dimensional strings vibrating in higher dimensional space. Our familiar four-dimensional space-time might be just a slice of a much larger, higher dimensional reality called the bulk. The extra dimensions of string theory are typically assumed to be compactified, curled up so small that we can't detect them directly. But some versions of string theory allow for large extra dimensions that might be accessible under certain conditions. If we could somehow access these extra dimensions, we might find shortcuts through higher dimensional space that could dramatically reduce travel times in our familiar three-dimensional world. The concept of brains, higher dimensional objects in string theory, suggests that our entire universe might be a three-dimensional membrane floating in higher dimensional space. Gravity might be able to propagate through the extra dimensions while electromagnetic forces and matter remain confined to our brain. This could explain why gravity is so much weaker than the other fundamental forces. If large extra dimensions exist, they might provide pathways for faster than light travel. Instead of traveling through our familiar three-dimensional space, we might find ways to take shortcuts through the higher dimensional bulk. The mathematics of string theory allows for such possibilities, though they remain highly speculative and far beyond our current technological capabilities. The holographic principle, emerging from black hole physics and string theory, suggests that all the information contained in a volume of space can be encoded on its two-dimensional boundary. This principle implies that our three-dimensional reality might be a holographic projection of information stored on a distant two-dimensional surface. If the holographic principle is correct, it fundamentally changes our understanding of space and the possibility of faster-than-light travel. Information about events throughout the volume would be instantly available on the boundary, potentially allowing faster-than-light access to information, if not to matter itself. The ADS-CFT correspondence, a specific realization of the holographic principle, demonstrates that certain theories of gravity in the bulk can be exactly equivalent to quantum field theories on the boundary. This correspondence has revealed deep connections between gravity, quantum mechanics, and information theory that we're only beginning to understand. Black holes present perhaps the most extreme examples of space-time curvature in nature. At the event horizon of a black hole, space-time is curved so severely that light itself cannot escape. Inside the black hole, the usual relationships between space and time break down completely. Time becomes space-like and space becomes time-like, creating conditions unlike anything else in the known universe. The interior of a black hole might contain closed, time-like curves, regions where it's possible to travel into your own past. If such regions exist, they represent natural laboratories for studying the relationship between space-time geometry and causality. However, the extreme conditions inside black holes make them inaccessible to any conceivable probe or explorer. Rotating black holes, described by the Kerr metric, have even more exotic properties. They drag space-time around with them as they rotate, creating regions called ergospheres, where nothing can remain stationary relative to distant observers. The mathematics of rotating black holes allows for the extraction of energy from their rotation, potentially providing enormous amounts of power for advanced civilizations. Some speculative proposals suggest that the interior of rotating black holes might contain traversable wormholes connecting to other regions of space-time. If such wormholes exist, they might provide natural, faster-than-light travel networks throughout the universe. However, the tidal forces near black holes would likely destroy any ordinary matter before it could reach these hypothetical passages. The concept of white holes, the time reverse of black holes, adds another wrinkle to our understanding of extreme space-time geometries. While black holes absorb everything that falls into them, white holes would explosively expel matter and energy. The connection between a black hole and a white hole through a wormhole is mathematically consistent with Einstein's equations, though no white holes have ever been observed. Cosmic strings, hypothetical one-dimensional defects in space-time left over from the early universe, could create their own exotic effects. If cosmic strings exist, they would have enormous linear mass density, creating significant gravitational effects despite being thinner than atomic nuclei. Two cosmic strings moving past each other at high speeds could create closed time-like curves, potentially allowing time travel. The energy scales involved in cosmic string interactions are comparable to those of the early universe itself. If we could somehow manipulate cosmic strings, we might be able to create the exotic space-time geometries required for faster-than-light travel. However, cosmic strings remain hypothetical, and even if they exist, they would be far beyond our ability to control or manipulate. Domain walls, two-dimensional defects in space-time, and monopoles, point-like defects, could create their own space-time distortions. These topological defects arise naturally in many theories of particle physics and cosmology. If they exist, They might provide natural laboratories for studying extreme space-time physics, though they would likely be as dangerous as they are exotic. The concept of space-time foam, proposed by John Wheeler, suggests that at the smallest scales, space-time itself might be constantly fluctuating and changing. Virtual black holes and wormholes might constantly form and dissolve at the Planck scale, creating a frothy, dynamic structure at the foundation of reality. If space-time foam exists, it might provide a natural mechanism for faster-than-light effects. Information might be able to tunnel through the microscopic wormholes in the foam, potentially allowing faster-than-light communication or travel. However, the effects would likely be random and uncontrollable, making them useless for practical purposes. The mathematics of general relativity allows for many exotic space-time geometries that seem to permit faster-than-light travel. Solutions like the Alcubierre drive, traversable wormholes, and closed time-like curves are mathematically consistent with Einstein's equations. However, the energy requirements for creating these geometries are typically enormous, often requiring matter with properties that we've never observed. The energy problem isn't just practical, it might be fundamental. The equivalence principle, which states that gravitational and inertial mass are identical, ensures that creating significant space-time curvature requires significant amounts of energy. There might be no way around this fundamental relationship between energy and curvature. Moreover, the stability of exotic space-time geometries remains questionable. Even if we could somehow create a warp drive or wormhole, quantum fluctuations might cause it to collapse before it could be used. The precise balance of forces required to maintain these structures might be too delicate to sustain in the face of inevitable quantum perturbations. The thermodynamics of space-time adds another constraint to faster-than-light travel schemes. Black holes have temperature and entropy, suggesting that space-time itself has thermodynamic properties. Any manipulation of space-time would have to respect these thermodynamic limits, potentially placing fundamental bounds on what kinds of geometries can be created and maintained. The second law of thermodynamics, which states that entropy always increases, might prevent the creation of the highly ordered space-time structures required for faster-than-light travel. Creating a warp drive or wormhole might require a decrease in entropy that violates this fundamental law of physics. Recent developments in quantum gravity and cosmology have revealed new constraints on space-time manipulation. The weak gravity conjecture suggests that gravity is always the weakest force, placing limits on how strongly space-time can be curved by electromagnetic or other non-gravitational forces. This might prevent the creation of the exotic matter states required for faster-than-light travel. The swampland conjectures emerging from string theory suggest that not all mathematically consistent field theories can be realized in a theory of quantum gravity. These conjectures place restrictions on what kinds of physics are possible, potentially ruling out the exotic matter and energy conditions required for faster-than-light travel. Even if we could overcome all these theoretical obstacles, the practical challenges of manipulating space-time would be staggering. We would need to control energies comparable to those of stars or black holes, manipulate matter at the quantum level with perfect precision, and maintain exotic energy conditions that might be fundamentally unstable. The engineering challenges are so severe that they might represent a new class of impossibility. Even if faster-than-light travel is theoretically allowed by physics, the practical requirements might place it forever beyond the reach of any conceivable technology. We might find ourselves in the strange position of knowing that something is possible in principle, while being certain that it's impossible in practice. Yet the history of physics is filled with phenomena that seemed impossible until we understood them better. Quantum mechanics seemed to violate common sense until we learned to think quantum mechanically. Relativity overturned our understanding of space and time until we learned to think relativistically. Perhaps our current understanding of space-time will similarly be overturned by future discoveries. The structure of space-time might be more flexible than we currently imagine. New physics beyond general relativity and quantum field theory might reveal mechanisms for faster-than-light travel that we can't currently conceive. The universe has surprised us before with phenomena that seemed impossible until we discovered them. But even as we explore these possibilities, we must acknowledge the enormous gulf between theoretical possibility and practical reality. The energy requirements for manipulating space-time remain far beyond anything we can imagine achieving. The exotic matter required for most faster-than-light schemes might not exist in nature. The quantum effects that govern space-time at small scales might prevent the precise control required for macroscopic manipulation. Perhaps most fundamentally, our current understanding of physics might be incomplete in ways that either make faster-than-light travel easier or rule it out entirely. We don't yet have a complete theory of quantum gravity, and such a theory might reveal new constraints or new possibilities that we haven't yet imagined. As we push against the boundaries of known physics, we're reminded that our understanding of space-time is still evolving. Each new discovery reveals both new possibilities and new constraints. The structure of space-time might hold the key to transcending the light speed barrier, or it might explain why such transcendence is fundamentally impossible. If light speed barriers could somehow be broken, what would this mean for our understanding of the universe and our place within it? The implications would extend far beyond physics into the deepest questions about the nature of reality itself. What would it actually feel like to travel at or beyond the speed of light? How would the universe appear to someone moving at these impossible speeds? These questions push us into a realm where physics becomes almost mystical, where our normal understanding of perception, distance, and time breaks down completely. The answers reveal not just the technical impossibilities of faster-than-light travel, but the profound ways it would transform our very experience of reality. Let's begin with what happens as you approach the speed of light. Imagine you're in a spacecraft, gradually accelerating toward this cosmic speed limit. At first, the changes would be subtle, noticeable only with precise instruments. But as you approach significant fractions of light speed, the transformation of your reality would become dramatic and unmistakable. From your perspective inside the spacecraft, everything would seem normal. Your body would feel the same, your thoughts would flow at their usual pace, and time would appear to pass normally. This is one of the most counterintuitive aspects of relativity. You never feel yourself slowing down or speeding up through time. Your own reference frame always seems perfectly normal to you. But the universe outside your spacecraft would undergo a bizarre transformation. Due to length contraction, distances in the direction of your motion would appear to shrink. Stars that were light years apart would seem to compress together. The entire cosmos ahead of you would appear flattened, as if someone was squeezing a three-dimensional universe into a pancake. At 90% the speed of light, distances would contract to about 44% of their original length. At 99% light speed, they would shrink to just 14%. As you approach light speed itself, the entire universe ahead of you would compress into an impossibly thin disk, with all the stars and galaxies appearing to lie in a narrow band around your direction of motion. But the visual effects would be even stranger than simple compression. Due to relativistic beaming and the Doppler effect, the light from objects ahead of you would be blue shifted to higher frequencies, while light from objects behind you would be red shifted to lower frequencies. At extreme speeds, visible light ahead might shift into dangerous ultraviolet or even X-ray radiation. The night sky would transform into something completely alien. The familiar constellations would disappear, compressed and distorted beyond recognition. Most of the universe would appear to glow with a brilliant blue-white light in front of you, while behind you, everything would fade to a dim red glow and eventually into invisible infrared radiation. More disturbing still would be the gradual disappearance of the outside universe. As you approach light speed, time dilation would cause the external universe to slow down from your perspective. Events that normally take seconds would appear to unfold over minutes or hours. The rotation of planets would slow to a crawl. The orbits of stars around galactic centers would become imperceptibly slow. If you could somehow reach light speed itself, the outside universe would appear to freeze completely. Time would stop for everything except you. You would exist in a strange limbo where the entire cosmos hangs motionless around your spacecraft. But this scenario is impossible because reaching light speed would require infinite energy and infinite time. From the perspective of someone watching your journey from Earth, your experience would be equally strange but in different ways. They would see your spacecraft gradually flatten in the direction of motion, becoming thinner and thinner as you approach light speed. They would see your time slow down, watching you age more and more slowly as your speed increases. At 99% light speed, 1 second on your spacecraft would correspond to about 7 seconds on Earth. At 99.9% light speed, the ratio would be about 22:1. Your journey to a nearby star might take just months from your perspective, but decades or centuries would pass on Earth. This time, dilation creates a profound asymmetry in the experience of space travel. You could travel to distant galaxies and return to find that millions of years had passed on Earth. Everyone you knew would be long dead. Entire civilizations would have risen and fallen, and the planet itself might be unrecognizable. High-speed space travel becomes a one-way journey through time as much as through space. But what if you could somehow exceed the speed of light? The mathematics of relativity breaks down at this point, but we can explore what the equations suggest would happen if faster than light travel were possible. The results are mind-bending and paradoxical. First, your relationship with causality would become confused. Events that you observe in one order might be seen in a different order by other observers. You might witness effects before their causes, see replies before messages, and experience a universe where the normal flow of cause and effect becomes scrambled. The relativistic Doppler effect would become even more extreme. Light from objects you're moving toward would be blue, shifted to unimaginable frequencies, potentially creating deadly radiation. But more fundamentally, the very concept of moving towards something becomes ambiguous when you're traveling faster than the light that carries information about that object. Your perception of distance would become paradoxical. In some reference frames, you would appear to arrive at your destination before you left your starting point. The concept of a journey through space would lose its normal meaning when the journey happens faster than information about it can propagate. Most disturbing of all, you might be able to observe your own past. If you could travel faster than light in a loop and return to your starting point, you might arrive before you left. You could potentially witness your own departure, creating a violation of causality that undermines our basic understanding of existence and identity. These paradoxes suggest that faster-than-light travel isn't just technologically difficult, it's conceptually problematic. It would require us to abandon our normal understanding of cause and effect, time and space, and even personal identity. The universe might simply not permit such violations of logic and causality. But let's explore what faster-than-light travel might mean for exploration and discovery. If we could somehow overcome these paradoxes, the universe would become dramatically smaller and more connected. Galaxies separated by millions of light years could be reached in human timescales. We could explore the cosmic web of dark matter, visit the centers of active galaxies, and observe the universe on scales impossible to reach at subluminal speeds. The psychological impact of faster-than-light travel would be profound. Our species has evolved with the constraint that distant events are ancient history by the time we observe them. The sun we see is 8 minutes old. The stars we observe show us the galaxy as it was years or decades ago, and distant galaxies reveal the universe as it existed billions of years ago. If we could travel faster than light, we might be able to observe events as they happen across cosmic distances. We could witness the birth of stars in real time, watch galaxies collide and merge, and observe the large-scale evolution of the universe as it unfolds. The cosmos would transform from a museum of ancient light into a living, dynamic entity we could explore and interact with. The cultural implications would be equally dramatic. Human civilization could spread across the galaxy and maintain real-time communication. Ideas, art, and culture could flow between star systems as easily as they flow between cities today. We could become a truly galactic species, united by faster-than-light communication and travel. But this connectivity would come with its own challenges. The diversity of human culture might be homogenized by instant communication. The isolation that allows different civilizations to develop unique characteristics would be lost. We might gain the galaxy, but lose the rich diversity that comes from separated development. The scientific implications of faster-than-light travel would revolutionize our understanding of physics. If such travel were possible, it would require new physics beyond Einstein's relativity. We would need to develop new theories of space-time, causality, and information that could accommodate faster-than-light phenomena while preserving logical consistency. Such theories might reveal that our current understanding of reality is fundamentally incomplete. Perhaps space and time are emergent properties of some deeper structure that allows for faster-than-light connections. Perhaps consciousness or information has properties that transcend the normal limitations of space-time. The search for faster-than-light possibilities has already led to important insights about the nature of space-time and quantum mechanics. Even if faster-than-light travel proves impossible, the theoretical exploration of these possibilities deepens our understanding of the fundamental structure of reality. Consider how faster-than-light travel would change our perception of cosmic scales. The observable universe extends about 46 billion light-years in every direction, not because space itself extends that far, but because that's how far light has been able to travel since the Big Bang. With faster-than-light travel, we might be able to explore regions of space that are currently beyond our observable horizon. We might discover that the universe is much larger and more complex than we currently imagine. Regions that appear empty in our telescopes might be teeming with galaxies and structures that we simply can't see because their light hasn't had time to reach us. Faster-than-light exploration could reveal the true scope and complexity of cosmic structure. The philosophical implications are equally profound. Our understanding of existence is deeply tied to our experience of space and time. If faster-than-light travel were possible, it would challenge fundamental assumptions about the nature of reality, consciousness, and identity. Would you still be the same person if you could travel backward in time and meet yourself? If multiple timelines exist simultaneously, which one represents the real universe? These questions push us beyond physics into deep philosophical territory about the nature of self and reality. The psychological experience of existing outside normal space-time constraints would be unprecedented in human history. We have no framework for understanding what it would feel like to move through time as easily as we move through space, or to exist in a state where causality becomes fluid and malleable. Perhaps most importantly, faster-than-light travel would fundamentally change our relationship with the cosmos. Currently, we're isolated inhabitants of a small planet connected to the universe only through ancient light and distant observations. Faster-than-light travel would make us active participants in cosmic evolution, able to explore, interact with, and potentially influence the development of the universe itself. But even as we imagine these possibilities, we must remember that they remain purely speculative. The barriers to faster-than-light travel aren't just technological, they're embedded in the fundamental structure of space-time itself. The universe seems designed to prevent the causality violations and logical paradoxes that faster-than-light travel would create. Yet the fact that we can imagine these scenarios, that the mathematics allows for such possibilities, even as physics constrains them, reveals something profound about the relationship between mind and reality. Our ability to conceive of transcending physical limits might itself be a kind of faster-than-light travel, a journey of imagination that crosses cosmic distances in the space of a thought. The speed of light keeps galaxies isolated and maintains the orderly flow of cause and effect that makes physical law possible. But it also creates a profound loneliness, trapping each world in its own sphere of causal influence. Faster-than-light travel would solve this cosmic isolation, but at the cost of undermining the logical structure that makes comprehension possible. These speculations shape both the science and the philosophy of our place in the cosmos, forcing us to confront the deepest questions about the nature of reality and our role within it. The quest to transcend the speed of light reveals something profound about human nature, our irrepressible drive to push beyond every boundary, to question every limit, and to imagine possibilities that stretch far beyond our current reality. This drive has propelled us from cave dwellers to space explorers, from primitive tool users to manipulators of quantum mechanics. But as we contemplate faster-than-light travel, we must ask ourselves deeper questions about the wisdom and ethics of pursuing technologies that could fundamentally alter the nature of existence itself. Throughout human history, our relationship with limits has been complex and paradoxical. We respect boundaries even as we dream of transcending them. We understand that constraints often define and protect what we value, yet we're driven to push against those very constraints. The speed of light represents perhaps the ultimate test of this relationship, a limit so fundamental that transcending it would require us to rewrite the basic rules of reality. Consider what drives our fascination with faster-than-light travel. At its core lies a deep dissatisfaction with cosmic isolation. We look up at the night sky and see a universe of staggering beauty and complexity, yet we're trapped on a single world, separated from the cosmos by distances so vast that light itself, the fastest thing in the universe, takes years or millennia to bridge them. This isolation feels profoundly wrong to our exploratory nature. But this desire for connection raises fundamental questions about the nature of exploration itself. Are we driven by genuine curiosity about the universe, or by a need to conquer and possess? Do we seek to understand the cosmos, or to bend it to our will? The motivations behind our dreams of faster-than-light travel reveal deep truths about our species and our relationship with the natural world. The philosophical implications of transcending light speed extend far beyond mere transportation. If we could travel faster than light, we would be manipulating the fundamental structure of causality itself. We would be assuming godlike powers over space and time, abilities that could reshape reality in ways we can barely comprehend. The question isn't just whether we could develop such technologies, but whether we should. The hubris involved in attempting to exceed the speed of light is staggering. We would be challenging limits that have governed the universe since its beginning, constraints that may be essential to the very existence of stable reality. The speed of light doesn't just limit how fast we can travel, it maintains the logical structure that makes existence possible. By attempting to transcend it, we might be risking the destruction of everything we seek to explore. This brings us to fundamental questions about the nature of knowledge and discovery. Science has always involved pushing against the boundaries of the known, but there's a difference between discovering what already exists and attempting to reshape the fundamental laws that govern reality. When we split the atom or decode DNA, we're uncovering natural processes, but faster than light travel would require us to violate or transcend natural law itself. The ethical considerations become even more complex when we consider the potential consequences of faster than light technology. If such travel creates the possibility of time paradoxes and causality violations, we might inadvertently destroy the logical consistency that makes rational thought possible. We could unleash forces that unravel not just our understanding of physics, but the very foundation of comprehensible reality. Imagine the responsibility that would come with wielding such power. A single mistake in faster-than-light navigation could potentially create paradoxes that ripple throughout space-time, affecting not just our present, but our past and future as well. We would be gambling with the stability of existence itself, and the stakes would be literally everything that has ever existed or ever could exist. The cultural and psychological implications are equally profound. Our sense of identity is deeply tied to our experience of linear time and local causality. We understand ourselves as beings who exist in a specific moment, who have a particular history, and who face an uncertain future. Faster-than-light travel could shatter this understanding, creating scenarios where we might encounter multiple versions of ourselves or witness events that challenge our basic assumptions about identity and continuity. Consider the moral implications of time travel, one of the inevitable consequences of faster-than-light travel. If you could go back and prevent a tragedy, would you have an obligation to do so? But what about the countless butterfly effects that such intervention might create? You might prevent one tragedy only to cause another, or save one life only to doom many others. The moral calculus becomes impossibly complex when causality itself becomes malleable. The concept of free will takes on new meaning in a universe where effects can precede their causes. If the future can influence the past, then the very notion of choice and agency becomes questionable. Are we really making decisions, or are we simply playing out predetermined roles in a cosmic script written by some future version of ourselves? The philosophical foundations of ethics and responsibility crumble when causality becomes circular. There's also the question of justice and equality in access to faster-than-light technology. Such capabilities would confer enormous power on whoever possessed them. They could observe any event in history, travel to any location instantaneously, and potentially manipulate the timeline itself. How could such power be distributed fairly? How could we prevent it from being used for oppression, surveillance, or worse? The environmental and cosmic implications are staggering to contemplate. If faster-than-light travel requires the manipulation of exotic matter or the creation of artificial black holes, we might be dealing with technologies that could accidentally destroy solar systems or galaxies. The energy scales involved in warping space-time significantly are comparable to those of stellar explosions or galactic collisions. One miscalculation could have consequences beyond imagination. But perhaps the deepest ethical question involves our relationship with the natural order itself. The universe has spent 13.8 billion years evolving according to certain fundamental rules. Stars have been born and died. Galaxies have formed and evolved, and life has emerged and flourished, all within the constraints imposed by the speed of light and other physical constants. Do we have the right to attempt to transcend these constraints? Are we showing admirable ambition or dangerous arrogance? The anthropic principle suggests that the physical constants of our universe, including the speed of light, are precisely tuned to allow for the existence of stars, planets, and life. If we attempt to manipulate these constants or find ways around them, we might be threatening the very conditions that make our existence possible. We could be, like children, playing with the foundations of the house we live in, unaware that we're undermining our own stability. Yet, there's also a counter-argument rooted in the history of human progress. Every major breakthrough in science and technology has initially seemed impossible or dangerous. Flight was considered impossible until we achieved it. Nuclear energy was unimaginable until we unlocked it. Genetic engineering seemed like science fiction until we made it reality. Perhaps faster-than-light travel is simply the next impossible thing waiting to become possible. The question becomes one of balance between ambition and wisdom, between the drive to explore and the responsibility to preserve. How do we pursue the most ambitious dreams of human exploration while respecting the fundamental structures that make such dreams meaningful? How do we push the boundaries of the possible without destroying the very possibility of boundaries? There's also the temporal dimension of responsibility to consider. If faster-than-light travel makes time travel possible, we would bear responsibility not just to our contemporaries but to all of human history. Our actions could affect the past, potentially altering or erasing entire civilizations. We would become guardians of all of time, carrying an impossible burden of responsibility across all of history. The psychological preparation required for such responsibility would be unprecedented. How do you prepare someone to wield power over space and time itself? How do you ensure that such capabilities are used wisely when the consequences of misuse could be the unraveling of reality itself? Traditional ethics and decision-making frameworks seem woefully inadequate for such scenarios. Perhaps most fundamentally, we must ask whether transcending the speed of light would truly serve human flourishing, or would instead transform us into something no longer recognizably human. Our entire evolutionary history has been shaped by the constraints of space and time. Our psychology, our cultures, our ways of understanding meaning and purpose all evolved within these limitations. By transcending them, we might lose essential aspects of what makes us human. The search for faster-than-light travel might be revealing a deeper psychological need, the desire to transcend not just physical limitations but mortality itself. Death is perhaps the ultimate speed limit, the final boundary that none of us can cross. Our dreams of conquering space and time might be expressions of our deepest fear of ending, our refusal to accept the ultimate constraint on human existence. But there's beauty in limitations, meaning in boundaries. The speed of light creates a cosmic horizon that preserves mystery and wonder. It ensures that the universe will always hold secrets beyond our immediate reach, maintaining the sense of awe and curiosity that drives scientific exploration. In trying to transcend this limit, we might be destroying one of the sources of what makes existence meaningful. The role of imagination in this quest cannot be underestimated. Our ability to conceive of faster-than-light travel, to imagine transcending fundamental physical limits, represents one of the most remarkable capabilities of human consciousness. Even if such travel proves impossible, the very fact that we can imagine it reveals something profound about the nature of mind and its relationship to reality. This imaginative capacity might be more important than any actual faster-than-light technology. Through imagination, we can already travel faster than light in the realm of thought. We can explore distant galaxies, visit alien worlds, and experience realities that transcend the constraints of physics. Perhaps this mental faster-than-light travel is more valuable than any physical equivalent could ever be. The ethical framework for approaching faster-than-light research must therefore balance multiple considerations. We must honor our drive to explore and discover while respecting the fundamental structures of reality. We must pursue ambitious goals while acknowledging the potential for catastrophic consequences. We must dream of transcending limitations while appreciating the value of boundaries. This requires a new kind of wisdom, one that can hold seemingly contradictory truths in tension. We must be bold enough to pursue the impossible, while being humble enough to accept that some impossibilities might need to remain impossible. We must be curious enough to explore every avenue, while being wise enough to recognize when exploration becomes destructive. The development of such wisdom might be more important than the development of faster-than-light technology itself. Learning to wield power responsibly, to pursue knowledge ethically, and to balance ambition with humility are challenges that extend far beyond physics into the deepest questions of human character and purpose. Perhaps the greatest value of contemplating faster-than-light travel lies not in achieving it, but in forcing us to confront these fundamental questions about the nature of knowledge, power, and responsibility. The journey toward understanding these limits teaches us as much about ourselves as about the universe. It reveals our deepest motivations, our greatest fears, and our most profound hopes. As we stand at the edge of what might be possible, we must choose carefully how to proceed. The decisions we make about pursuing technologies that could transcend fundamental physical limits will define not just our future, but potentially our entire past and the very nature of reality itself. This awesome responsibility demands the highest levels of wisdom, humility, and ethical reflection. The conversation about faster-than-light travel is ultimately a conversation about what it means to be human in a universe that is both magnificent and constraining, both open to exploration and bounded by fundamental limits. How we navigate this conversation will determine not just whether we ever transcend the speed of light, but whether we remain worthy of the cosmic gifts we already possess. Speculation aside, humanity's path forward depends on what we discover about the universe and ourselves, not just what we dream of conquering or transcending. While we dream of transcending the speed of light, the universe offers us countless wonders within the boundaries that physics has established. Perhaps the most profound exploration isn't about breaking cosmic speed limits, but about discovering what's possible within them. The future of human exploration might be less about conquering fundamental forces and more about working creatively within the magnificent constraints that define our reality. The technologies emerging today are already transforming our ability to explore the cosmos, even while respecting the speed of a light barrier. Artificial intelligence is revolutionizing how we process astronomical data, discovering patterns and phenomena that human astronomers might never notice. Machine learning algorithms can analyze light curves from distant stars, identifying subtle signals that indicate the presence of exoplanets or exotic astrophysical phenomena. These AI systems don't need to travel faster than light to explore the universe. They can sift through terabytes of data from space telescopes, ground-based observatories, and radio dishes, extracting information about cosmic structures billions of light years away. In a sense, we're already exploring the distant universe through the ancient light that carries messages across cosmic time. Every photon that reaches our telescopes is a faster-than-a-light messenger from the past, telling us stories about the universe as it existed long ago. Quantum computing represents another revolutionary tool for cosmic exploration. These machines could simulate the behavior of exotic matter, model the interior dynamics of black holes, and perhaps even help us understand the quantum nature of space-time itself. While quantum computers won't directly enable faster-than-light travel, they might reveal new physics that could change our understanding of what's possible within the cosmic speed limit. The computational power of quantum systems might allow us to simulate entire universes, exploring scenarios and physical laws that we could never test directly. We could model what happens inside event horizons, investigate the behavior of matter at densities exceeding those in neutron star cores, and explore the quantum mechanics of space-time itself. This computational exploration could be as revealing as any physical journey through space. Fusion power, still tantalizingly beyond our current capabilities, could transform space exploration by providing the enormous energy densities needed for relativistic travel. While fusion won't let us exceed the speed of light, it could enable us to reach significant fractions of light speed, making interstellar travel possible within human lifetimes. A fusion-powered spacecraft traveling at 10% light speed could reach Proxima Centauri in about 43 years, opening the door to direct exploration of nearby star systems. But even fusion power presents enormous engineering challenges. The energy required to accelerate a spacecraft to relativistic speeds is staggering. To reach 10% of light speed, the kinetic energy alone would be equivalent to detonating thousands of hydrogen bombs. Managing such energies safely while maintaining life support systems would require technological breakthroughs that dwarf our current capabilities. the concept of generation ships offers a more conservative approach to interstellar exploration. Instead of trying to reach high speeds quickly, we could build massive spacecraft designed to sustain human populations for centuries or millennia. These ships would be miniature worlds, complete with ecosystems, manufacturing capabilities, and cultural institutions that could preserve human civilization across the vast gulfs between stars. Generation ships raise profound questions about identity and purpose. The people who arrive at distant star systems would be descendants of those who began the journey, separated by dozens of generations from the original explorers. They would be citizens of the ship rather than Earth, with cultures shaped by centuries of life in artificial environments. In a sense, the journey itself would become the destination, the ship a traveling civilization, exploring both space and the evolution of human society. Breakthrough propulsion concepts like solar sails and laser-propelled light sails offer more immediate possibilities for interstellar exploration. These systems could accelerate small spacecraft to significant fractions of light speed using photon pressure from stars or powerful laser arrays. While the payloads would be tiny, perhaps no larger than smartphones, they could carry sophisticated sensors and communication equipment capable of transmitting detailed information about distant star systems. The Breakthrough Starshot project envisions sending thousands of postage stamp-sized spacecraft to Proxima Centauri using laser propulsion. These tiny probes could reach 20% of light speed, arriving at our nearest stellar neighbor in just 20 years. While they couldn't carry human passengers, they could return the first close-up images and measurements of an exoplanet, transforming our understanding of worlds beyond our solar system. Even within our own solar system, robotic exploration is revealing wonders that challenge our understanding of planetary science and astrobiology. The moons of Jupiter and Saturn are turning out to be complex worlds with subsurface oceans, active geology, and possibly even life. Europa, Enceladus, and Titan represent targets for exploration that could answer fundamental questions about the prevalence of life in the universe. These worlds don't require faster than light travel to reach. They're accessible with current or near-future technology, offering opportunities for discovery that could rival any interstellar expedition. The search for life in our own solar system might reveal that biology is far more common and resilient than we previously imagined, suggesting that the universe is teeming with life even if we can't reach it quickly. Mars continues to beckon as the most accessible target for human expansion beyond Earth. While Mars missions won't reveal new physics or test the boundaries of space-time, they would represent a crucial step in becoming a multi-planetary species. The technologies developed for Mars exploration, from life support systems to in-situ resource utilization, would lay the groundwork for more ambitious missions to the outer solar system and eventually to other star systems. The psychological and cultural aspects of space exploration are as important as the technological ones. How do we maintain human morale and purpose during journeys that last decades or centuries? How do we preserve scientific objectivity and cultural diversity in isolated spacecraft communities? These challenges require innovations in psychology, sociology, and governance that could be as revolutionary as any breakthrough in propulsion technology. Virtual and augmented reality technologies offer intriguing possibilities for space exploration. Astronauts on long-duration missions could experience simulated environments that provide psychological relief from the confines of spacecraft. More ambitiously, virtual reality could allow us to explore the universe through the sensors of robotic probes, experiencing distant worlds as if we were physically present while remaining safely on Earth. Telepresence technology could enable real-time exploration of planetary surfaces using robotic avatars controlled by human operators. While signal delays limit this approach within our solar system, advanced AI could compensate for these delays, allowing for quasi-real-time exploration of worlds that would take decades or centuries to reach with human crews. The concept of digital consciousness raises even more speculative possibilities. If human consciousness could somehow be uploaded to digital systems, space exploration could transcend the biological limitations that constrain flesh and blood astronauts. Digital explorers could survive the radiation, vacuum, and extreme temperatures of space while processing information and making decisions at computational speeds far exceeding biological thought. But digital consciousness remains deeply speculative, raising profound questions about the nature of mind and identity. Would a digital copy of a human consciousness truly be the same person, or would it be something entirely different? These questions push us into philosophical territory that's as challenging as any physics problem. More practically, advances in robotics and artificial intelligence are creating increasingly capable, autonomous explorers. Robots don't need life support, don't experience psychological stress from isolation, and can be designed to survive environments that would instantly kill human explorers. Future robotic missions could include sophisticated AI systems capable of making complex decisions, conducting scientific experiments, and even repairing themselves using local materials. Swarm robotics offers another approach to space exploration. Instead of sending single large spacecraft, we could deploy fleets of small, interconnected robots that work together to explore planetary surfaces, asteroid belts, or the interstellar medium. These swarms could be self-organizing and self-repairing, with individual units that can be lost without compromising the mission. The search for extraterrestrial intelligence represents a form of exploration that transcends physical travel entirely. By listening for signals from other civilizations, we're essentially exploring the universe for evidence of intelligence and culture. The detection of an alien signal would transform our understanding of our place in the cosmos more profoundly than any physical journey to distant stars. SETI research is advancing rapidly with new telescopes, signal processing techniques, and theoretical frameworks for detecting technosignatures. We're learning to look for subtle signs of alien technology, from atmospheric pollution on exoplanets to megastructures around distant stars. These searches require no faster than light travel, yet they could reveal the presence of civilizations throughout the galaxy. The development of self-replicating spacecraft, sometimes called von Neumann probes, represents perhaps the most ambitious concept for exploring the galaxy within the speed of light constraint. These spacecraft would travel to other star systems, use local materials to build copies of themselves, and then send those copies to even more distant systems. Given enough time, such probes could explore the entire galaxy without ever exceeding relativistic speed limits. Self-replicating probes raise their own challenges and risks. How do we ensure they remain under human control across interstellar distances and timescales? What happens if their replication goes awry, creating exponentially reproducing machines that consume entire star systems? The concept offers enormous potential for exploration, but also enormous risks that would need to be carefully managed. Biotechnology offers another avenue for space exploration that works within physical constraints. Instead of trying to transport Earth life to other worlds, we might engineer organisms specifically adapted for alien environments. These biological explorers could survive on Mars, in the oceans of Europa, or in the hydrocarbon lakes of Titan, conducting research and perhaps even terraforming these worlds for future human habitation. Synthetic biology could create organisms that serve as living spacecraft, growing their own hulls, producing their own fuel, and repairing damage using biological processes. These bioships would blur the line between technology and biology, creating new categories of exploration vehicles that are as much alive as they are engineered. The concept of digital archaeology represents an intriguing approach to exploring the past without time travel. By analyzing the subtle traces left by ancient events, we might be able to reconstruct the history of the universe in unprecedented detail. Gravitational waves carry information about cosmic events billions of years in the past. The cosmic microwave background preserves echoes of the early universe. Future technologies might allow us to extract vastly more information from these ancient signals. Neutrino astronomy is already revealing hidden aspects of the universe, detecting particles that travel essentially unimpeded from the cores of stars, supernovae, and black holes. Future neutrino detectors could provide real-time views of the universe's most energetic processes, allowing us to observe phenomena that are invisible to traditional telescopes. The exploration of consciousness itself might prove as rewarding as the exploration of space. Understanding how consciousness arises from matter, how it processes information, and how it creates the experience of reality could reveal new principles that reshape our understanding of everything from quantum mechanics to cosmology. The space between our ears might contain mysteries as profound as the space between the stars. Perhaps most importantly, the exploration of sustainability and planetary stewardship right here on Earth represents a crucial frontier for human development. Learning to live sustainably within Earth's ecological limits, developing technologies that enhance rather than degrade natural systems, and creating cultures that value long-term flourishing over short-term exploitation are challenges that will determine whether we survive long enough to explore the stars. Climate science, renewable energy, ecosystem restoration, and sustainable development might seem mundane compared to faster-than-light travel, but they're the foundation that makes any space exploration possible. We need to prove we can be responsible stewards of one planet before we're trusted with the resources of many. The integration of all these approaches, from AI and quantum computing to robotic swarms and biological engineering, suggests that the future of exploration will be far richer and more diverse than any single breakthrough in faster-than-light travel could provide. Instead of seeking one magical technology that transcends physical limits, we're developing an entire ecosystem of capabilities that work creatively within those limits. This distributed approach to exploration might be more robust and ultimately more successful than any attempt to break the speed of light barrier. By developing multiple pathways to knowledge and discovery, we're ensuring that human curiosity and exploration can continue, regardless of which specific technologies succeed or fail. The universe offers us countless ways to explore and discover without requiring us to violate fundamental physical laws. From the quantum realm to cosmic scales, from the deep past to the far future, from the nature of matter to the mystery of consciousness, we have frontiers enough to occupy human curiosity for millennia to come. Even within light speed limits, humanity's reach into the cosmos is expanding slowly but surely, opening new chapters in the greatest story ever told. The universe gradually awakening to its own existence through the eyes and minds of conscious beings who dare to look beyond their small world toward the infinite mystery that surrounds them. As we stand at the threshold of technologies that could reshape the fundamental nature of reality, we face responsibilities unlike any our species has ever confronted. The pursuit of faster-than-light travel and the manipulation of space-time itself brings us to a precipice where our choices could echo across all of time and space. This awesome power demands a corresponding level of wisdom, humility, and ethical reflection that challenges us to become worthy of the cosmic forces we seek to understand and potentially control. The history of human technological development is filled with examples of discoveries that seemed purely theoretical until they suddenly became world-changing realities. Nuclear physics began as an abstract investigation into the nature of atoms and ended with weapons capable of destroying civilization. Quantum mechanics started as a curious puzzle about blackbody radiation and led to computers, lasers, and technologies that define the modern world. Genetic engineering emerged from basic research into DNA structure, and now gives us the power to redesign life itself. Each of these breakthroughs forced humanity to grapple with new forms of responsibility. Nuclear weapons required us to develop concepts of mutual assured destruction and global arms control. Genetic engineering demands new frameworks for bioethics and safety. Computer technology has created challenges around privacy, artificial intelligence, and the transformation of human society. But the potential development of faster-than-light travel would dwarf all previous challenges, requiring us to think responsibly about power over the fundamental structure of reality itself. The first principle of cosmic responsibility must be the recognition that not every theoretical possibility should be pursued practically. The fact that mathematics allows for certain exotic space-time geometries doesn't automatically mean we should attempt to create them. Some knowledge might be too dangerous to implement, some powers too great for any finite beings to wield responsibly. Learning to say no to certain possibilities might be as important as learning to say yes to others. This principle challenges our deepest assumptions about the value of knowledge and discovery. We've been taught that knowledge is always good, that understanding is always better than ignorance, and that technological capability should always be developed if it's possible. But faster-than-light travel forces us to confront the possibility that some knowledge might be too dangerous for our current level of wisdom and maturity. Consider the temporal paradoxes that faster-than-light travel could create. If we could influence our own past, we would face decisions that could affect not just our future, but the entire history of the universe. Every choice would carry the weight of potentially altering or erasing countless lives, civilizations, and realities. The moral calculus becomes incomprehensibly complex when causality itself becomes malleable. How do we prepare decision makers for such responsibility? Traditional ethics assumes a linear progression from cause to effect, from decision to consequence. But in a world where effects can precede causes and where future decisions can influence past events, our entire framework for moral reasoning breaks down. We would need to develop new forms of ethics, capable of handling circular causality and temporal paradoxes. The energy scales involved in faster-than-light travel create another dimension of responsibility. The manipulation of space-time requires energies comparable to those of stars or black holes. A single miscalculation could potentially destroy solar systems, disrupt galactic structures, or trigger cascading effects that propagate throughout the universe. We would be working with forces so powerful that the margin for error approaches zero. This brings us to questions about the proper scale of human ambition. Throughout our history, we've gradually expanded our sphere of influence from individual actions to tribal effects to global impacts. Climate change represents our first truly planetary scale challenge, requiring us to think about consequences that affect the entire Earth system. Faster-than-light travel would expand our potential impact to cosmic scales, making us responsible for effects that could ripple across space and time. The development of such technologies would inevitably be concentrated in the hands of a few individuals, institutions, or nations. How do we ensure that cosmic scale powers are used for the benefit of all humanity, rather than for narrow interests? How do we prevent faster-than-light technology from becoming a tool of oppression, surveillance, or warfare? The same capabilities that could enable benevolent exploration could also be used for monitoring, controlling, or even eliminating perceived threats across all of space and time. International cooperation becomes crucial when dealing with technologies that could affect the entire universe. No single nation or organization should have unilateral control over faster-than-light travel, yet the coordination required for global oversight would be unprecedented. We would need governance structures capable of making decisions that bind not just current generations, but all possible future timelines. The precautionary principle suggests that when dealing with technologies that could have catastrophic consequences, we should err on the side of caution. But faster-than-light travel challenges even this principle. The potential benefits of such technology could be so enormous that they might justify significant risks. The ability to explore the universe, contact alien civilizations, and transcend the limitations that currently confine us to a single planet might outweigh the dangers of temporal paradoxes and space-time instability. This creates a profound moral dilemma. How do we weigh the enormous potential benefits of faster-than-light travel against the catastrophic risks? How do we make decisions about technologies when the consequences could include the destruction of causality itself? Traditional risk assessment frameworks seem inadequate when the stakes include the logical consistency of reality. The question of timing becomes crucial. Even if faster-than-light travel is theoretically possible, it doesn't follow that we should pursue it immediately. Perhaps we need to develop greater wisdom, better international cooperation, and more sophisticated ethical frameworks before we're ready to wield such power. The technology might need to wait for our moral and political development to catch up with our scientific capabilities. But this raises its own challenges. How do we maintain scientific curiosity and technological progress while imposing limits on research directions? How do we prevent promising lines of investigation from being abandoned due to excessive caution? The balance between prudence and progress requires careful navigation, especially when the potential rewards are so transformative. The role of public engagement in these decisions cannot be overstated. Technologies that could affect the fundamental nature of reality shouldn't be developed in secret by small groups of scientists and engineers. The entire human species has a stake in decisions about faster-than-light travel, and everyone deserves a voice in determining whether and how such technologies should be pursued. This requires unprecedented levels of public education about complex physics and ethics. How do we help people understand concepts like space-time curvature, causality violations, and exotic matter well enough to participate meaningfully in decisions about their development? How do we maintain democratic governance over technologies that require deep expertise to understand? The generational dimension of responsibility adds another layer of complexity. Decisions about faster-than-light travel could affect not just current generations, but all future ones. If we create temporal paradoxes, we might be altering or erasing the existence of countless future people. Do we have the right to make such decisions on behalf of generations not yet born? Conversely, if we choose not to pursue faster-than-light travel, we might be condemning future generations to permanent cosmic isolation. The stars will continue to move away from us due to cosmic expansion, making them increasingly difficult to reach even at high speeds. Our current epoch might represent a brief window when interstellar travel is possible, and delaying too long could close that window forever. The environmental dimension of cosmic responsibility extends far beyond Earth. If we develop technologies capable of manipulating space-time, we would become responsible for the cosmic environment itself. Our actions could affect the structure of space and time throughout the universe, potentially disrupting natural processes on scales we can barely comprehend. This cosmic environmentalism would require us to think about the universe as a system to be preserved and protected rather than simply exploited. Just as we've learned to consider the ecological impact of our actions on Earth, we would need to consider the space-time impact of our actions on the cosmos. The universe has spent billions of years evolving complex structures like galaxies, stars, and planets. Do we have the right to risk disrupting these structures in pursuit of faster-than-light travel? The question of alien life adds another dimension to these considerations. If intelligent life exists elsewhere in the universe, our experiments with faster-than-light travel could affect them as well. Space-time disturbance created in our solar system could propagate throughout the galaxy, potentially disrupting alien civilizations or even threatening their existence. This brings us to questions about cosmic citizenship and our obligations to potential alien neighbors. Even if we never directly contact extraterrestrial intelligence, our actions could affect them through the manipulation of space-time itself. We would need to develop frameworks for considering the interests of beings we may never meet in decisions about technologies that could affect the entire universe. The possibility that advanced alien civilizations might already possess faster-than-light technology creates additional complexities. If such civilizations exist, they might have strong opinions about newcomers attempting to develop these capabilities. Our experiments could be seen as threatening, destabilizing, or simply naive by beings with millions of years more experience manipulating space-time. This suggests the need for cosmic humility in our approach to faster-than-light research. We might not be the first species to grapple with these challenges, and we could potentially learn from the wisdom of more advanced civilizations. But this requires us to acknowledge that our perspective might be limited and that we might need guidance from beings with greater experience. The role of scientific integrity becomes crucial when dealing with technologies of such enormous potential impact. Researchers working on faster-than-light physics must be completely honest about uncertainties, risks, and limitations. The pressure to oversell results or downplay dangers could lead to catastrophic miscalculations when dealing with forces that could affect the entire universe. This requires new standards of transparency and accountability in scientific research. When the stakes are cosmic, traditional peer review and publication processes might be insufficient. We might need new institutions and procedures specifically designed to oversee research that could have universe-altering consequences. The psychological preparation required for cosmic responsibility is unlike anything in human experience. How do we prepare individuals to make decisions that could affect all of space and time? How do we maintain mental health and perspective when dealing with literally infinite consequences? The cognitive and emotional demands of cosmic responsibility could exceed human psychological capabilities. This might require new approaches to education, training, and decision-making that help people cope with responsibilities of cosmic scale. We might need to develop new forms of collective decision-making that distribute the psychological burden across many individuals rather than concentrating it in a few leaders. The spiritual and philosophical dimensions of cosmic responsibility are equally important. Many of the world's wisdom traditions speak of the interconnectedness of all existence and the responsibility of conscious beings to act with compassion and wisdom. These ancient insights might provide crucial guidance as we navigate the challenges of wielding cosmic-scale powers. The development of faster-than-light technology would force us to confront fundamental questions about the nature of existence, consciousness, and our role in the universe. Are we meant to transcend physical limitations, or are those limitations essential to what makes us human? Do we have a cosmic destiny that requires us to spread throughout the universe? Or should we focus on deepening our understanding and appreciation of our current situation? Perhaps the greatest responsibility we face is the obligation to become worthy of the powers we seek to develop. This might require us to evolve not just technologically, but morally, spiritually, and psychologically. We might need to become fundamentally different kinds of beings before we're ready to wield the forces that govern space and time. The timeline for this evolution is uncertain. It might take generations or millennia for humanity to develop the wisdom needed to handle faster-than-light technology responsibly. This suggests that the pursuit of such capabilities should be measured in centuries rather than decades, allowing time for our moral and spiritual development to keep pace with our technological capabilities. But even as we contemplate these enormous responsibilities, we must remember that the choice might not be entirely ours. Other nations, organizations, or even individuals might pursue faster-than-light research regardless of ethical considerations. This creates pressure to develop such technologies defensively to ensure that they're in responsible hands rather than falling to those who might use them irresponsibly. This defensive rationale has driven many dangerous technological developments throughout history, from nuclear weapons to biological warfare agents. The logic is seductive but potentially flawed when applied to faster-than-light travel. The risks might be so great that it's better to ensure no one develops these capabilities, rather than trying to ensure they're in the right hands. The international dimensions of cosmic responsibility require unprecedented cooperation between nations, cultures, and institutions. We would need to develop new forms of global governance capable of making decisions about technologies that could affect the entire universe. This might require us to transcend traditional concepts of national sovereignty in favor of cosmic citizenship. The educational challenges are equally daunting. How do we prepare future generations to think responsibly about cosmic scale powers? How do we teach the complex physics, ethics, and philosophy required to understand these issues? The curriculum for cosmic citizenship would need to integrate science, philosophy, psychology, and spirituality in ways that traditional education has never attempted. Perhaps most importantly, we must cultivate the humility to recognize when we're approaching the limits of our wisdom and capability. The universe has existed for nearly 14 billion years without human intervention, developing complex structures and processes that we're only beginning to understand. The assumption that we can improve on this natural development by manipulating fundamental forces might represent dangerous hubris. This humility doesn't require us to abandon all ambition or curiosity. Instead, it suggests that we should approach cosmic-scale technologies with the reverence and caution they deserve. We should proceed slowly, carefully, and with constant attention to the enormous responsibilities that such capabilities would entail. The pursuit of faster-than-light travel forces us to confront the deepest questions about knowledge, power, and responsibility. It challenges us to become not just better scientists and engineers, but better human beings. The universe might be testing whether we're ready to join the cosmic community of intelligent civilizations, and our response to this test will determine not just our technological future, but our moral and spiritual destiny. In the end, whether or not faster-than-light travel is possible, the very act of contemplating it responsibly transforms us. It forces us to think on cosmic scales, to consider our obligations to all existence, and to grapple with questions that push us beyond our current understanding of ethics and responsibility. This transformation might be more valuable than any technology we could develop, preparing us for a future where human consciousness spans the stars, not through faster-than-light travel, but through the expansion of wisdom, compassion, and understanding. The meaning of discovery itself becomes transformed when we accept these cosmic responsibilities, shifting from conquest and exploitation toward reverence, stewardship, and the patient cultivation of wisdom, worthy of the infinite mystery that surrounds us. The stars remain distant tonight, their light still bound by the cosmic speed limit that has governed the universe since its beginning. Above us, photons that began their journey years, decades, or millennia ago complete their long voyage to our eyes, carrying messages from a cosmos that stretches far beyond our immediate reach. Yet through science, philosophy, and imagination, we have somehow managed to reach back toward those distant lights, touching infinity with finite minds. Our journey through the mysteries of faster-than-light travel has taken us to the very edges of physics and beyond, into realms where mathematics becomes poetry and speculation transforms into philosophy. We've explored the rigid barriers that relativity erects around the speed of light, examined the exotic loopholes that might exist in the fabric of space-time itself, and contemplated the profound responsibilities that would come with transcending the fundamental limits of reality. What have we discovered in this exploration? Perhaps the most important insight is that the question of faster than light travel is really about much more than transportation or technology. It's about the nature of limits themselves, about human ambition and cosmic humility, about the relationship between what we can imagine and what we can achieve. The speed of light barrier forces us to confront deep questions about the structure of reality and our place within it. The mathematical possibility of faster than light travel through exotic space-time geometries reminds us that the universe might be far stranger and more flexible than our everyday experience suggests. The Alcubierre drive, traversable wormholes, and other speculative concepts show us that physics allows for possibilities that stretch our imagination while remaining tantalizingly beyond our technological reach. These concepts exist in the liminal space between dream and reality, challenging us to think beyond conventional limitations. Yet the enormous energy requirements, the need for exotic matter, and the causality paradoxes that plague faster than light travel also remind us that nature seems designed to protect certain fundamental principles. The speed of light isn't just an arbitrary limit, it's woven into the logical structure that makes reality comprehensible. The universe appears to resist attempts to violate causality or create logical contradictions, suggesting a deep wisdom in the cosmic order that we're only beginning to appreciate. The exploration of these limits has revealed something profound about human nature itself. We are beings who cannot help but push against boundaries, who dream of transcending every constraint, who find meaning in the very act of reaching toward the impossible. This drive has taken us from caves to computers, from earthbound creatures to space explorers, from ignorance about the cosmos to detailed maps of galaxies billions of light years away. But our investigation has also shown us the importance of working creatively within constraints rather than simply trying to smash through them. The technologies emerging today, from artificial intelligence to quantum computing to fusion power, offer pathways to cosmic exploration that respect physical law while expanding our reach in extraordinary ways. The universe offers us countless wonders to discover without requiring us to break the fundamental rules that govern reality. Perhaps the most valuable discovery of our journey is the realization that imagination itself might be a form of faster than light travel. In the space of a thought, we can traverse cosmic distances, visit alien worlds, and explore possibilities that transcend the boundaries of physics. Our minds can journey to places that our bodies may never reach, experiencing realities that exist only in the realm of consciousness and creativity. This mental faster than light travel might be more important than any physical equivalent. Through imagination, we can explore infinite worlds without consuming infinite energy. We can experience transcendence without violating causality. We can touch the cosmic without risking the destruction of logic itself. The boundaries that physics imposes on matter and energy don't seem to apply to consciousness and imagination. The questions we've explored tonight will likely outlive our current civilization. Whether faster than light travel is ultimately possible or impossible, the pursuit of understanding these limits will continue to drive scientific inquiry and philosophical reflection for generations to come. Each advance in physics, each new insight into the nature of space-time, each technological breakthrough will shed new light on these fundamental questions. Future generations might discover new physics that makes faster than light travel routine. Or they might prove conclusively that such travel violates principles so fundamental that it's forever impossible. Either discovery would transform our understanding of the universe and our place within it. The journey toward understanding is as valuable as any destination we might reach. What seems certain is that the speed of light will continue to serve as both barrier and inspiration, defining the boundaries of the possible while illuminating the infinite creativity required to work within those boundaries. The cosmic speed limit challenges us to be more ingenious, more patient, and more thoughtful in our approach to exploration and discovery. The responsibility that comes with contemplating these cosmic forces has transformed us in ways that might be more profound than any technological breakthrough. Thinking seriously about faster than light travel forces us to consider our obligations to all existence, to grapple with powers that could affect the entire universe, and to develop wisdom worthy of cosmic citizenship. This transformation of consciousness might be the real gift of our journey. Tonight, as we look up at the stars, we can appreciate them not just as distant lights, but as participants in the grand story of cosmic evolution. Each photon that reaches our eyes has traveled across space and time to connect us with the universe beyond our small world. The speed of light isn't just a barrier, it's the medium through which the cosmos communicates with itself, allowing stars to reach across the darkness and touch our awareness with their ancient light. The conversation between mind and cosmos continues in both directions. While starlight carries information to us across vast distances, our thoughts and dreams reach back toward those distant suns with a speed that transcends any physical limit. In the realm of consciousness, the universe becomes small enough to hold in a single thought, immediate enough to experience in a moment of wonder. Whether we ever develop faster than light travel or remain forever bound by relativistic limits, we are already citizens of the cosmos through our capacity for understanding, imagination, and awe. We carry the universe within us in the form of consciousness that can contemplate infinity, love that can transcend distance, and curiosity that knows no bounds. The stars remain distant, their light slow to reach us, carrying messages from the deep past about cosmic events we can only imagine. Yet through science, philosophy, and imagination, we reach them nonetheless, bridging the gap between finite existence and infinite mystery with the fastest thing in the universe, the human capacity for wonder itself. The speed of light may stand unbroken, but the boundaries of human curiosity stretch infinitely beyond any cosmic speed limit, illuminating possibilities that exist not in the realm of matter and energy, but in the unlimited landscape of consciousness exploring its own cosmic home.